In the next 6 minutes, you are going to understand all these equations and variables with their concept. So let's begin. Since the caveman ages, humans have never been particularly smart, but they have been doing something that we are still following millions of years later, blowing something hot to make it cold. Today, we are actually going to understand the thermodynamics behind this puff of air. First of all, this phenomenon is actually forced convection, but we will start with heat transfer. The basic definition of heat transfer is if there is some temperature difference, then heat will flow. Let's take an example of a cup of coffee and understand. In this cup of coffee, you can see the coffee inside is very hot, due to which the heat would be transferred to the cup. Now, that cup will transfer the heat to the tea plate. Why? Because there is the temperature difference. And because both of them are same material, or you could say same medium, that is solid, so this mode of heat transfer is conduction. Now, coming to our main focus, that is convection. Like I just explained a bit earlier, the coffee is transferring heat to the cup. Both are of different mediums, and the coffee is also transferring heat to the atmosphere above it. That is also two different mediums. Hence, it is convection. Just the only difference between convection and conduction. Now let's understand convection in a bit better way as it is our main focus. Convection is of two types: forced convection, natural convection. The only difference being if there is no interference at all, then it is natural. If there is, then it is forced. We are actually going to compare both of these things to actually understand how effective is actually blowing a hot food. Does it actually work? We are going to understand the thermodynamics behind it. But before going to physics, we need to understand the boundary condition. It simply means the assumptions that we are taking, nothing more than that. Almost all the assumptions are already here. I just want you to understand the physical significance between H and K. These two coefficients are actually directly proportional with the heat that is getting transferred. If more heat is getting transferred, then these things will increase. For example, in a metal bar, the K, the conductive coefficient, would be much higher than a ceramic plate. Pretty simple example. And exactly same concept with H. We actually need H here. We already have the K because we know the the property of the ceramic cup, but we need H here. So now we are going to understand some dimensionless constant which are very important here to actually understand the calculation behind it. The first dimensionless constant that we would be looking at would be Reynolds number. Understand this as the inertial force and viscous force ratio. Inertial force means, let's say the cup is at moment. Everything is actually continuously at moment. And to stop it, you will need to give some force. That is the inertial force. To understand viscous force, understand it as the denseness of the fluid. For example, cement is much more dense than air. Simple, this is a kind of oversimplified manner, but you can understand it this way. We actually need Reynolds number to determine whether the fluid is laminar or turbulent. Laminar means you cannot actually see the disturbance, but in turbulent you can actually see, and that is the number that we have that will give us if it is laminar or turbulent. But you can see that is external and internal, and in this image now you can see what is the difference between external flow and internal flow. Now obviously we are going to follow the external flow. You can just rewind back to see what are the values. Now we will do the calculation, which is velocity into density into diameter into divide by the viscosity. And as you can see, it is laminar. Now we will go to Prandtl's number. Let's take a simple bathtub as an example. Now in this bathtub, let's at any point as marked in that thing, you dip your finger or something. Then you will see waves forming like in this bad animation of mine. But you understand. Now how fast this thing actually gets in the liquid, in the fluid, that is the momentum diffusion. Because if you do this exact same thing in cement, again it will be very slow or just not possible, so it has a very less momentum diffusion. Now the heat diffusion is also exactly the same. It is actually the, you could say, conductivity of the fluid itself. It is the speed in which any temperature disturbance will transfer the heat towards the end of the fluid. Like just in the diagram, if you dip something hot in that end, how fast it will reach to the other end. So that's a pretty simplified way in which you can understand. Now we will get to the last dimensionless constant, that is the Nusselt's number. understand it as the ratio between the heat transfer and the conduction. And you can see it is actually equivalent as we are also multiplying the diameter there. But anyways, Nusselt's number actually has two formula. One that I just discussed, the second one is for turbulent and annular. If you actually see the equation properly, you will notice we already have all the values except for h. We will use this formula to calculate what would be the value of h. From this we will calculate what would be the actual heat transfer. So before you go to the calculation, you already have all the formulas. Now applying the calculation, you will get this answer exactly. Now finally we have our heat transfer coefficient, which we will use, multiply it with the surface area and temperature difference. You will finally have your forced convective heat transfer. And the formula that we are using here is simple Newton's law of cooling. We don't need to deep dive here a lot, but this is just understand this is the law that we're using. Anyways, for natural convection, benefit of the doubt, you can see this thing because it would be very complicated for now. But this is the simple concept in which natural convection works. The hot air goes above because of the less density, and the cold air recycle backs. Now the coffee will again transfer the heat to it, and this cycle repeatedly goes on. Anyways, following the calculation that I showed you in the image, you can see, of course, the forced convection is greater. So finally, we have the answer why we blow something hot. Hope you learned something from this. Thank you.